we did an example of a hypothesis test for a population mean when we know the standard deviation of the population. And now we are going to do a hypothesis test for a population mean when we don't know the standard deviation of the population. As a reminder, when we don't know the standard deviation of the population, but we have an approximately normal population, or when we have a large enough sample size, then we have to use the student's t-distribution. The nice thing about the technology in ArtofStat is that there is an app for inference for the mean that uses the t-distribution. So for this one, I will use the app for inference of a mean. Unfortunately, there is no normal distribution for the inference of the mean, so I can't use this app when I do a hypothesis test or a confidence interval for a normal distribution for the population of the sample means, for the distribution of the sample means. So this is going to be a much quicker test and more straightforward since we already have the technology for this. If you use your calculator, if you use Excel, you will use the t-distribution to do your tests. So statistics students believe that the mean score of the first statistic test is 65. A statistics instructor thinks the mean is higher than 65, and he samples 10 statistics students and obtains the following scores. He performs a hypothesis test using a 5% level of significance, and the data are assumed to be from a normal distribution. So for here, the instructor claims the alternative hypothesis that the mean is greater than 65, and the students believe theoretically that the mean is equal to 65 or less than or equal to 65. But for now equals. There is no evidence in this scenario that the students believe that it is less than or equal. The level of significance is 5%, 0.05, and our random variable will be the mean exam score. Measured in points. However, when we sketch our t-distribution, the t-distribution will have t-scores corresponding to the variable, which is the mean exam score in the statistics class. The t-distribution will have 0 here, and then tick marks that may go beyond 3 away from the mean. And especially if we have a small sample, we do. So the distribution is a t-distribution. The sample size is 10. So the degrees of freedom are equal to n minus 1. The t-distribution will be a t-distribution with 9 degrees of freedom. And I will just copy these scores and enter them in ArtofStat. So here in ArtofStat, I will do a confidence interval and significance test. I will pick here that I will do a significance test. For this case, I will enter my own data right here. The name of the variable is the mean exam score, or maybe I should say just exam score. And the observations are these guys, separated by spaces. And I am looking for a right tail test. So this alternative hypothesis greater than 65 indicates a right tail test. And I need to find what is the sample mean and what test statistic that provides, what kind of t-score that provides. But ArtofStat will do that for me. So for the null value of the mean, we want to say that this is 65, and we need the alternative hypothesis to be greater than. and it will tell us that this is the t-distribution. It does go a little further than 4 and -4 on the tails. Our test statistic is a t-score that happens to be 1.978. So somewhere close to 2. This way, 1.978. I should have been a little closer to 2, but it's fine. There. And the p-value, which is this area to the right of my test statistic of 1.978, comes out to be 0.0396, almost 4%. So the p-value is 0.0396. We have a significance level of 5. So 5% to the right in the right tail would be considered unlikely or unusual. We do have a 3% or almost 4%. So 0.0396 is an unlikely event from this theoretical distribution of a mean of 65 for a sample score of 10 statistic students, and therefore I have enough evidence to reject the null hypothesis. The conclusion is that at the 5% significance level, the sample data provides sufficient evidence that the mean exam score will be greater than 65. Again, notice here that in my decision, I either reject the null hypothesis or fail to reject the null hypothesis. In my conclusion, I start with a significant level, and then I determine whether I have enough evidence to support the alternative hypothesis, or if I don't have enough evidence to support the alternative hypothesis. If I reject the null hypothesis, I can support the alternative hypothesis. So my conclusion states that at the 5% significant level, the sample data provides sufficient evidence to support, and then I describe the alternative hypothesis. Also pay attention to the fact that both the null and the alternative hypothesis are talking about the mean of the population. So I have to state that I'm talking about the true population mean exam score for the first statistics test, and then state the null hypothesis that claims that that mean is greater than 65. Remember that we have two other ways of actually solving the hypothesis test. We can solve it with the critical value of a t-score. So basically try to find for the level of significance of 5%, what is the t-score that determines the beginning of the right tail, t of alpha to the right, that will contain the 5% of t-scores that I'm allowed to basically discard, and they would produce a type 1 error, but I am allowed to consider those as unlikely. So this will be alpha, the area, and I need this t-score. If my test statistic t of 1.978 is in that critical area, then it is considered an unusual outcome from the theoretical distribution, and therefore I can reject the null hypothesis that is the theoretical distribution. So if my sample, which is the evidence I collect, is in this critical area, then in the critical interval of t-scores, then I can reject the null hypothesis. So the question is, how do I find this critical value? And to do that, I need to go to the art of stat t-distribution. And I want to find a percentile quantile. Over here, it asks me for the degrees of freedom. Remember that the degrees of freedom are 9. Also, you can ask your art of stat inference for population mean app to show you the degrees of freedom here. So you can see them that they are 9, or you can remember that they are n-1. I am looking for an upper tail, and I want the probability in the upper tail to be 5%. And I will get the critical value for t to be 1.833. So this t that determines the critical region is 1.833, and the test statistic that I found ended up being in the critical region. It was 1.978. Remember, how do we find the t-score? This test statistic is the x bar we have minus the mean of the population divided by the standard deviation, the standard error of the distribution. So my x bar would be the mean of the test scores. And again, in the inference for the mean, it told us that the sample mean ended up being a 67. So art of stat actually did this math. Our theoretical mean was the null value, which is a 65, and the standard error, the sample standard deviation was 3.20, but the standard error was ended up being 1.01 because it was 3.20 divided by the square root of 10. So if I do the math in my calculator, I don't need to because art of stat did it for me, but this answer 3.20, so this was the little s, I guess, since we are using the t-distribution because we don't know the population standard deviation divided by the square root of 10. And this is how I found this 1.978, which art of stat found for me. So again, my test statistic ends up being in the critical region. That indicates that the sample data are unusual if the theoretical distribution were true, and therefore the decision is to reject the null hypothesis. The conclusion is still the same. At the 5% significance level, the sample data provides sufficient evidence to support the claim that the true population mean exam score for the first statistics test is greater than 65. Remember also that we can use a third method of doing a hypothesis test, and that is to find a confidence interval centered around the mean, the sample mean, and if we can capture in the confidence interval the population mean, then we cannot reject the null hypothesis. But if the population mean is too far out of the confidence interval and cannot be captured, then we have sufficient evidence to reject the null hypothesis. Now again, if you want to create a confidence interval that has 5% probability on the right tail, then the confidence interval is a two-tail test. You need a 5% on the left tail. Remember that your confidence interval is centered about your x bar, but luckily the art of stat app for the inference of the mean can also give you a confidence interval here. If you want it to be two-sided and you want that probability to be 90%, so that every tail can have a 5% probability. We do give our own data. The data is already logged in. The sample mean is the center of my confidence interval, and the standard error is 1.01 with a t-score of 1.85 and with a t-score of 1.8333, if you remember, and a margin of error t-score times the standard error of 1.85. So it created this confidence interval for me, which is 65.15 to 68.85. So I will do a 90% confidence interval, and it was from 65.15 to 68.85. And this confidence interval does not include the theoretical mean exam score, which was 65, and therefore I have evidence to reject the null hypothesis. Remember, my decision is whether I will reject the null or fail to reject the null. My conclusion will only mention the alternate or alternative hypothesis. So my conclusion is that at the 5% significance level, the sample data provides sufficient evidence to support the claim that the true population mean exam score for fair statistics test is greater than 65. Notice again here that the claim you are supporting is the alternative hypothesis. So when you say the claim and you state this claim here, this claim is exactly your alternative hypothesis, that the mu, which is the population mean, is greater than 65.